Cyclic voltammetry is an electrochemical technique that is widely used to investigate the reduction and oxidation behavior of species. It allows us to find out at which potential these reactions occur, and besides, it is possible to analyze how much electrons are involved in the reaction, as well as the reaction rate under which the electrons are transferred. To find out how it works, it is best to show that along the voltammogram that is recorded during the measurement. But first, what kind of equipment is being used? Bringing electrons to the system, we need to have a sophisticated power source, a galvanostat or potentiostat. This power source slowly increases the voltage in a certain time while measuring the current. The materials that we would like to analyze are typically put on the working electrode, and the current is then measured of electrons coming from or going to the counter electrode. The actual voltage is measured towards a reference electrode to allow comparing the results with other materials. In more detail, cyclic voltammetry involves applying an increasing potential, swept linearly with respect to time, from an initial value to a final value and then back to the initial value. The response of the electrochemical system is then a plot of the resultant current against the applied potential to produce this voltammogram. A plot displays the current versus potential and provides detailed information about the oxidation and reduction process. In the forward scan, the oxidative scan, the reaction starts as soon as a current is observed and stops once all species have reacted, and thus the current becomes zero. In the ideal case, the backward scan, the reductive scan, is exactly the same, but then the measured current becomes negative. The maximum of the peak is seen as the potential of the actual reaction. Unfortunately, the oxidation and reduction reactions do not occur at the same potential, but are shifted. The oxidative peak to higher voltages and the reductive peak to lower voltages. This shift has to do with the delay of the reaction and can be regarded as a source of internal resistance of the reaction. Hence, it provides valuable information about the kinetics of the redox process and the electrochemical reversibility. For a reversible reaction, this peak separation is relatively small, but in practice the shift can be significant. If the electron transfer faces more resistance, the establishment of the equilibrium takes longer and therefore leads to a larger peak separation. These larger peak separations suggest slower electron transfer kinetics and a quasi-reversible or irreversible process. It may also happen that the reaction has not completely finished before we reach the maximum voltage. The result is a duck-shaped graph. Remember that the voltage increase is scanned in a certain time, which means that the surface area under the graph can be regarded as the number of electrons that have been transferred, hence a capacity Q. This can easily be seen by the simple equation of time t times the current I, which reflects capacity. The capacity of the oxidation reaction is the surface area underneath the curve at the positive current of the forward scan, here indicated by the light blue part, but also by the additional surface area at the backward scan at positive current, here indicated by the dark blue part. Notice that this last part needs to be added for the capacity of the oxidation reaction, because as long as the current is positive, the oxidation reaction takes place. The capacity for the reduction starts once the current becomes negative, and that is shown here with the orange part. Obviously, in this example, the oxidation capacity is bigger than the reduction capacity. This will mean we will lose some capacity during scanning forward and backward. Another interesting parameter that can be analyzed using cyclic voltammetry is the diffusion coefficient of the migration electroactive species. This can be done by using the so-called Randall-Sevcik equation, which relates the peak current IP to the diffusion coefficient D of the electroactive species. We then need to scan at various scan rates V. Then the peak current is equal to the square root of the diffusion coefficient times the square root of the scan rate times a constant C. This constant C contains the number of electrons involved in the oxidation reaction, the electrode area, and the concentration of the electroactive species. The voltammogram at lower scan rate gives lower maximum currents. This is understandable because the scan rate is dependent on time and the capacity was equal to time times current. Therefore, a lower scan rate has a lower time and thus gives us a lower peak current. In summary, the mathematical models create the basis for analyzing the cyclic voltammetry data and obtaining important parameters that describe the electrochemical processes taking place. The models can be used to provide information about electrochemical kinetics. Parameters such as peak current, peak potentials and peak shapes can be used to determine rate constants, electron transfer coefficients and reaction mechanism. This data aids in the understanding of the reaction mechanisms of the electrochemical systems involved. The diffusion coefficients obtained from the Randall-Sevcik equation gives a relationship between the current and scan rate. This provides insight into the mobility and transport of species within the electrochemical system. By examining the voltammogram, one can infer the electrode surface characteristics such as double layer capacitance, surface area and absorption processes. This information in characterizing the interaction of the electrode with the electrolyte. By comparing multiple cycles and observing the changes in the voltammogram, one can deduce the stability of the electrochemical species. Shifts in the peak current also points to the reactivity of the electrochemical species.